All right, you're welcome to today's lecture with From Eternity the Schoolboy, tutorials with From Eternity the Schoolboy. Please, I want to see your face. Shift this chair so that I want to see your face. Let me show you are following. All right, thank you. So today we are going to take a look at chemistry, and we'll continue from where we stopped in solubility. In our last class, we stopped at determination of what? Solubility, right? And we carry out experiment, even though we did not practicalize it. It's more like it's more of a alternative to what? Practical, or test of what? Practical. We carried it out to really explain how to determine the what? Solubility of what? Substances, specifically that of potassium 225 at room temperature, and water was used as the what? Solvent. Now after that, we gave assignment which we have reviewed. Now today we are going to start from solubility curve. Today we are going to start from where? Solubility curve. Are we together? Our reference book for today is New School Chemistry for Senior Secondary School by Oseyo Ababio, revised by L.E.S. Banisi, 2016 edition. So now, if you plot a graph, if you plot a graph of solubility of substances or solutes against their respective temperature, you get a what? Solubility what? Curve. If you plot, I said, solubility curve is a curve obtained when you plot a graph of the solubilities of a solute in a given solvent, in a given solvent against their respective what? Temperatures. I said that solubility curve is a curve obtained when you plot a graph of the solubilities of a solute in a given solvent against their respective what? Temperatures. I said that I'm trying to explain or define solubility curve. I said that solubility curve is a curve obtained when you plot solubilities of a solute in a given solvent against their respective what? Temperature. You know when you dissolve a solute in a solvent, right? If you dissolve a solute in a solvent to form a solute at a particular temperature, as you change the temperature of the solute, as you move to a particular temperature, you will get a different what? Solubility. Are we together? Look at the assignment we did. At 55 degrees Celsius, what did we get at the solubility of the solute? 6 moles. Put it in dm cube, becomes what? 30 moles per dm cube. True of us. At 55 degrees Celsius, the solubility of that solute is what? 30 moles per what? dm cube. But at 40 degrees Celsius, the solubility becomes what? 25 moles per dm cube. Have you now seen that at different temperature, the solutes will have different solubilities? True of us. Now, if you now plot these different solubilities of that solute against their respective temperature, you plot this. If you plot a graph now, and on the vertical axis you have solubility, on the horizontal axis you have what? Temperatures. That means, let's assume you plot this thing now. Let's use this small thing now we did here and plot a graph. of solubility against what? Temperature. We determine that shall we determine that at 55 degrees Celsius the solubility is what? 30 what? Moles per what? dm cube. At what? At 40 degrees Celsius the solubility is what? Is what? 25 moles per what? dm cube. Now if you can plot this graph now, graph of this is what? On y-axis you have your what? Solubility. On x-axis you have what? Temperature in what? Degrees Celsius. This one is in what? Mole per dm cube. Now let's assume here is 0, right? Let's assume the first one. Let's assume the first one here is what? Let's assume on the solubility side you have 10, we have 20, we have 30, we have what? 40. On the temperature side you have 10, 20, 30, 40, 50, 60. Now if you plot this thing guys, see what you will get. At 55 degrees Celsius, okay, let's start. When the solubility is 30, right? The temperature was what? 55. Somewhere here, right? That means the point of it should be here, right? True of us. Now, when the solubility at 40 degrees Celsius, the solubility becomes what? 25. Between 20 and 30 is what? 25. Here is 40, right? So this will be also somewhere what? Here. Now, if you plot this thing now, you get you get something like this. This is a solubility what? Curve. Hello? This now plotted now is called what? Solubility what? Curve. That's why I define solubility curve as the curve obtained when you plot a graph of the solubilities of a solute against their what? Respective what? Temperature. Is it clear? Is it clear? Good. This type of curve is called what? Solubility what? Curve. Now let's continue. Let's continue. Can someone tell me what we can deduce from this solubility? Can someone tell me what you can deduce from this solubility? The major thing, in summary, the key point you can deduce from this, what this curve shows. The main thing the curve shows. Who can tell us? Huh? What? Good. In summary, you can say the effect of temperature on what? Solubility. Period. Summary. Okay? The effect of temperature on what? Solubility. The effect of temperature on what? Solubility. That's what it shows. You understood what I said about this solubility curve, right? Is it confusing? Now, this solubility now, this curve you are seeing there now, even though they didn't mention a particular solute involved, but this curve is for one solute. One solute. It may be sodium chloride, it may be potassium chloride, it may be any solute, but just one solute at different temperature in a particular what? Solvent. Sometimes you may have a plot, you may have a curve, you may have a graph like this that may have up to 10 curves. You may have a graph like this that may have up to 10 curves, 10 different curves. Some may go like this, some may go like this, some may go like this, some may even go like this, straight, some may go like this, like this. These different curves represent different what? Solutes. So sometimes you may want to use one graph like this that to compare the solubility of different solutes at different temperature in the same what? Solvent. Is it clear? Such graph also exists. Now, for example, now you may have the one that, let me use one here as an example. You use the same solvent at the same temperature to check the different solute you use. Let's assume you bring potassium chloride. Water is solvent you want to use for all of them. Potassium chloride, potassium trichloride 5, potassium triazochlorate 5, sodium chloride, all those different solutes. But use the same water, which is the same amount of water. Am I complicating? Now you dissolve it in water. You check, you check the solubility in the same temperature. When you are done with this one, in the same temperature, you know the solubility and plot the graph. The same axis, you try for another solute using the same water at the same temperature. You plot the graph. You plot it on the same axis. You get the same axis. You get something like this. This will be for this may be for sodium chloride. This may be for potassium chloride. This may be for different what solutes. Does it make sense? Now I want to I want to put what I explain now in a graphical form for you to understand what I'm talking about. Now look at this graph now. Look at this graph now. Look at this graph now. Here is this place is what? Solubility, right? This is what? Solubility. It may be gram per watt, 100 gram. It may be mole per dm cube as case may be, okay? It may be mole per dm cube as case may be, depending on what the one you choose to use. And this space is what? Temperature in what? Degrees what? Celsius. Now let's assume here we have 20, 40, 60, and here we have, here is 0, 20, 40, 60, 80, and what? 100 degrees Celsius. From 0 degrees Celsius to 100 degrees what? Celsius. Now look at the first curve. Maybe you get something like sodium chloride, more potassium chloride. If you get something like potassium chloride and dissolve it in this amount of water, maybe any amount you want to use, but my focus is on this curve. You are the one that know the amount to use, and you trace the solubility. If you calcium hydroxide, this graph is from our reference book for today. I want to use it to explain something. You get something like this. This graph is for what? Calcium what? Hydroxide. This graph is for what? Calcium what? Hydroxide. Calcium what? What was an name for calcium hydroxide? Slake what? Slaked line, right? Good. Now, this is for, you see the curve for calcium hydroxide. This means something. I will explain what it means, okay? It goes like this and go like this. Now, you test the solubility. What it means is that you check the solubility, you increase the temperature, right? Yeah. You dissolve it in water. A particular amount in a particular amount of, I follow you. Yeah. In a particular amount of water, then you keep checking the solubility at different temperature. At the end, you plot the graph like this. This means something. I will explain. Now, you now do that of potassium triazochlorate 5. Potassium triazo what? Chlorate what? 5. See it here. You get something like this. It goes like this and increases like this. The formula for potassium triiodochlorate 5 is KCl O what? Good. What it means is that as you dissolve it and change the temperature, the graph, if you plot it, it will go like this. That's what it means. We are using the same solvent. This is solubility, and check it to be at this temperature. You know you change the solubility, you put it at this temperature, you change solubility. This is what you will see. Now let's check another solute, something like sodium tetraoxosulfate 6 decahydrate. You have something like this. You know, I taught people about water of what? Crystallization, right? But sodium tetraoxosulfate 6 decahydrate is a hydrated salt that has 10 molecules of what? 10 moles of what? Water of what? Crystallization. But we have the anhydrous one. Anhydrous means that it doesn't have any what? Water of what? Crystallization. So we also have anhydrous sodium tetraoxosulfate what? 6. Now, you go like this. First of all, it has two parts. The solubility will increase with temperature until you get to 36 degrees Celsius. Like this. You get to this place. It will go down like this. This what you see when you are using this amount on the same classes, the same amount you are using, the same everything in the same solvent. This is what you get. This part is 36 degrees Celsius. This part is what? Sodium tetraoxosulfate 6 what? 4 deca what? Hydrates. Why this side is a anhydrous one? It's called what? Simply what? Sodium what? Tetraoxosulfate what? 6. This is what you get from what? Sodium sulfate. Both the hydrated one and the what? Anhydrous what? One. Now let's look at what you get with sodium, potassium. No, let's finish all the sodium. Sodium chloride. For sodium chloride, it just threads one. It means something. For sodium chloride, it just threads from here. Just thread like this. No curve like this. It means something. So here is what? Sodium what? Chloride. I will explain the meaning of all these curves. Now, when you have something like, let's move to some potassium solute, salt. Let's look at potassium triiodochlorate 5. This one starts like this and just fast it increases with what? Temperature. Now, from here you can hear something like this. This was potassium what? Triiodochlorate 5. The formula is what? K what? NO what? 3. This is potassium triiodochlorate 5. Now you do the same thing again. Let's look at potassium chloride. Potassium chloride doesn't go steep like this. It goes like this. It starts here, but the same straight line. It goes like this. This one is what? Potassium what? Chloride. Are we together? Now let's look at another curve. Curve for I think is from what I have here is complete. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. I have 8 here. 1, 2, 3, 4, 5, 6. Is it 7? 1, 2, 3, 4, 5, 6, 7. It's complete. Now look at this curve now. I mean, I said if you look at it now, it will be complex. It looks complex, right? But the way I broke it down, do you understand it? This is what you call what? This one has a lot of. This one is we use this type of curves to compare solubility of different what solute in the same word graph. This is actually different curves of different graphs that they were brought together using the same axis. That's why it's like this. Does it make sense? So if you open your new school chemistry to read, don't get confused when you see something like this. Have you opened it in your new school chemistry? But you have new school chemistry. So what have you been reading? You've not read the Solubility we are taking in this class. Go to your new school chemistry and open it and try to read it. After this class, you will understand this better. Okay? Now I want you to put this in down. When you are done, I will now go to what each of these represents. Be fast, so we can finish before 6 p.m. Be fast. Right. Now let me explain this curve. So in order to explain this curve, there's what we call deduction. Now we talk about the deduction from the what curve. What I mean by deduction is what you can understand or what you can get from the what curve. Now let's take them one after the other. Let's take all the solutes one after the other. Now let's look at this solute. Look at these two curves now. I want to explain something about these two curves. I want to explain something about the curve of potassium trioxide 25 and the curve of see it here like this, and the curve of potassium what triosochlorate what 5. Look at this curve. I mean, are you aware that when you plot a graph, it goes like this? I want to ask you something. This is solubility and this is temperature. Listen carefully. And this is the same solubility what temperature. If you have a curve like this, I have a curve like I have a curve like this. What does it mean? What does the first one mean? It steps down like this, goes down like this. From solubility, it goes down like this. And it goes up from zero or whatever or any or vertical intercept and go up. What does it mean? What does this curve mean? Do you know? If you step slowly, if you step down like this, what does it mean? See what it means. This first one means that the solubility is inversely proportional to what? Temperature. That's what we do variation. What it means is this: as solubility increases, temperature decreases. That's the meaning of this curve. Are we together? But this one that goes up like this means what? That solubility is directly proportional to what? Temperature. As solubility increases, temperature is what? Increases. Now look at this thing. Now let me also write another graph. If you have a curve like this is solubility and this is what? Temperature. And like this. Do you know what it means? What it means is that the solubility is independent of what? Temperature. If temperature like, let it increase to 1 million. You know, this temperature increases like this, right? What does it mean that if temperature like, let it increase to Kafanchan, solubility cannot change because of it. Am I together? That's the meaning. What it means that solubility is independent of the what? Temperature. That's the meaning. If it is horizontal, if the horizontal line cuts the solubility and keep going towards this without even touching temperature side, what means that solubility is not dependent on what? Temperature. If temperature like, let it keep increasing. Solubility will remain what it is. Are we together? Now look at it. When solubility is 40, look up. When temperature is, let's assume that solubility is 40 here. So when temperature is 20, solubility is set for 40. When temperature is 50, is the same what? 40. So what it means that solubility is not dependent on what? Temperature. But in here, solubility depends on temperature, but that solubility increase as temperature increases. Look at it. Look at it here now. Here is 1 temperature. Here is 1 solubility, right? Here is 1 temperature. Here is 2. So as temperature increases, solubility is what? Increases. But look at this place. Look at this place. Look at this place. Here is temperature, right? Yes. And here is what? Here is the temperature. Look at it. Temperature is here. Here is 1, right? Yes. Here is 2, 5 for solubility, right? 4, 1, 0, right? Temperature is 1, 2, 3 to what? 4. When temperature is 1 here, watch out. Where will you touch the solubility? 5. When temperature is 2 increasing, where will you touch solubility? 4. That means solubility is what? Decreasing. Is it clear? Is that not an inverse? Is it not the direct? But this one has no correlation, no relationship. It's just it's on its own. It doesn't depend on what it. Is it clear? Is it clear? Good. So sometimes JAM may set this question without even writing any number and ask you which one is direct and which one is inverse. Have you seen anything like this before? Some they may ask for, they may so that they may write that place you have S. They may write volume V. Here is V. They will ask you which of this is Charles law. From your knowledge of Charles law, if here is V and here is T, first one. If here is P and here is T, here is V. Which do you think it should be Charles law? Direct, right? Okay. Volume and what? Temperature, right? Good. We are not treating gas law here, but I just want to use it to explain something. Now, if you understand this perfect now, let's interpret this what? Curve. Now look at potassium nitrate. Look at curve of potassium nitrate and curve of potassium chloride. What do you say? Okay, potassium chloride 5. Look at it. Okay, see what you do. Now let's compare. Let's look at these 3 curves now. Look at curve of potassium chloride 5. Look at curve of potassium chloride. Look at curve of potassium chloride 5. And look at curve of sodium tetrahydrogenase of a 6 decahydrate. What can you deduce?
That as the temperature increase, the solubility decrease.
Good. Is what?
Yeah?
Is what?
Decrease.
What are you saying?
No, as temperature increase, solubility increase.
Are you doing guesswork? Are you sure what they're saying?
I'm sure what I'm saying.
Based on what I explained here, right?
Yes.
So now, what if you look at the curve of potassium nitrate 5, curve of potassium chloride, curve of potassium triazochlorate 5, and curve of sodium tetrahydrogenase of a 6 decahydrate, they are all going up like this, right?
Yes.
That means that the solubility, as temperature increases, their solubility what? In water increases. Now, but they are not increasing at the same rates. Which one do you think increases very fast from this graph?
Very fast. And potassium triazonitrate.
Perfect. It's up, followed by what?
Potassium chlorate, triazochlorate 5.
No. Potassium chloride, got it. Full. Then potassium chlorate 5. But sodium tetrahydrogenase increase and start decreasing. I will explain why it happened. Now let's make the deduction. Having explained it better now, having laid the foundation, let me now tell you the deduction. Now, the first deduction is this. Number one. Solubility, the solubility of look at them. The solubility of potassium triazochlorate 5. This one. The solubility of potassium triazochlorate 5. You may just write the symbol so you don't waste time. The solubilities of potassium triazochlorate 5 and potassium triazonitrate 5 increase very rapidly with increase in what? Temperature. Is it clear? They increase very rapidly with increase in what? Temperature. See them. This one and what? Especially this and this. Is it clear? Is it clear?
Yes.
Now look at the curve. I want to ask a question now. Look at the curve for what I've explained so far. Look at the curve of sodium chloride and the curve of calcium hydroxide. What can you deduce from their curve?
That is independent of temperature.
Good, because there are this. If temperature like later you increase to 1 million degrees Celsius, they remain where they are. Just like this. So that means you don't need high temperature for sodium chloride to do what? Dissolve. If you get sodium chloride, salt to use, put in water, do you need high temperature? Once you put in water, you just dissolve it. You don't need to heat it, right? It doesn't need high temperature. It will dissolve at this space without even. If you like, increase the temperature, it will dissolve the way it want to do what? Dissolve. But if you increase temperature for potassium nitrate, triazole nitrate 5 and potassium triazole chloride 5, the more you increase temperature, the more they dissolve faster. That's the meaning. Am I making sense?
The more you increase
temperature, the more they dissolve. Am I making sense? Do you now appreciate solubility? Good. Now that's for. So you have said it now that sodium chloride, the covers from the covers sodium chloride and the calcium hydroxide, their solubilities are independent of what? Temperature. So you can put it down. Right. The solubilities of sodium chloride and calcium hydroxide are independent of what? Temperature. Are you aware that this can form a wonderful exam question? They will just draw a diagram like this without talking too much. You ask question on it. Are you aware? Alright, so please learn it now. Now look at the curve of potassium chloride. Look at the curve of potassium chloride. I want to point out the difference between that of potassium chloride. See it here. I want to point out the difference between that of potassium chloride, potassium nitrate 5 and what? I want to point. It's also fast, but I want to point out there's a difference between them. Any idea? Any idea? Any idea? Now, let me tell you why. Let me explain what happened. Look at the curve of potassium 5. It's fast. Look at potassium chlorate. It's fast, but it's not constant. Anytime you see a straight line, piam, it is uniform. True of us. Is what? Uniform at a constant rate. But potassium 5 like this goes like this. That of chlorate goes like this. That they are not at constant what? They increase, but are not at constant what? Rate. But that of potassium chloride increase at constant what? Rate. That's why it's straight like this. Yeah. Are we together? It increases at what? Constant. These curves are not the same. If you see a curve like this, let me show you. Even though they are direct, one that goes like this, and one that goes like this, they are direct, but they're not the same thing. This one is what? At constant. It's constant. It's uniform at constant rate. Are we together? But this one in this curve is not at constant what? Rate. The rate varies, but it's still what? Increase. It's still what? Direct. But this one is what? At constant rate. But this one is not constant. Am I communicating? Is it clear? Now that's why we can deduce from this curve of potassium chloride that solubility of potassium chloride increases at what? A constant rate with rise in what? Temperature. The solubility of potassium chloride increases at a constant rate with the rise in what? Temperature. The solubility of potassium chloride increases at a constant rate with the rise in what? Temperature. Is it clear? Good. Let's continue. Now, I want us to compare the curve of calcium hydroxide and curve of sodium chloride. Look at something. Let me run that out here again. Sodium chloride is just straight. Bam. Can you notice it? But calcium hydroxide is like this. True of us. Just as what we have here. Even though they have a relationship, but this one, there's something happened that made it to be like this. I will explain. Now, for calcium hydroxide, basically, are you aware that calcium hydroxide curve shows? Okay, now let me ask a question. Which of these salts, solutes, show lowest solubility? Solubility, yeah. That's why calcium hydroxide in real life has a very low what? Solubility. Amount is low. It's not that soluble in water. That's why it's not that soluble in water. In fact, it has low solubility. Now look at something. Look at it now. It has the lowest what? Solubility among all these salts. That's one thing I want you to point out about calcium hydroxide here. Then another thing I want you to point out and to put down is this. It shows a decrease in what? Solubility at temperatures over. Look at. Even though it's totally independent, it's independent of temperature. Altogether. But look at it. When you get to temperature of about from 70 degrees Celsius up, the solubility decreased. Look at it. It was constant too. But when you get to temperature from here, above what? From where? 70 degrees. Look at it. At this point, the temperature did what? Decreased. So at temperature of 70 degrees and above, the temperature did what? Decrease. Am I completing? That's one thing. What explanation of this what? They call for what? Calcium what? Hydroxide. We have touched all the other salts here, right? We have touched all the soil. Not salt. Solute. We've touched all the solutes here. Now, but we have not touched what? Sodium tetrahydrosulfate 6 decahydrate and sodium tetrahydrosulfate 6 anhydrous. This one that looks like funnel. Let's explain why it's like that. Okay, something caused it. It increased there and got here, and decreased. True of us, something caused that, and the exact temperature is stopped. Is start decreasing. Is at what? Passes what? Look at this. There's a reason for that. I will explain now. Now, are we together? So what? Okay. Sodium tetrahydrosulfate 6 shows. You see it now. You show the solubility curve that have a sharp break. You show the curve that have a sharp break at what? 36 what? Degrees Celsius. So why does it have that sharp break? That's what I want to explain. In a solution, hello, do you want to put down the first statement I made? I said that sodium tetrahydrosulfate 6 from the graph, sodium tetrahydrosulfate 6 curve shows a what? A sharp break at the temperature of what? 36 degrees Celsius. Now ask a question. Why did he have a sharp what? Why does it show a sharp break at 30 degrees Celsius? That's what we want to explain. You can ask it as a question. Why does it show a sharp break? So you will understand it when you're reading it again. Now let me explain why it has a what? Sharp break. Now, are you together? Are you together?
Yes.
Good. We said that the sharp break happens at what? 36 what? Degrees Celsius. Now listen. The first thing I want you to know: sodium tetraoxide 6. Sodium tetraoxide 6 salt in solution exists as a decahydrate at temperature below 30 degrees Celsius. So see what I mean. This salt we call what? Sodium tetraoxide 6. In a solution, when the solution is at temperature below 30 degrees Celsius, below what? Below what? When the temperature of each solution, let's assume now, hello, are you together? Let me explain before you write. If you get sodium tetraoxide 6 in a solution, and at a temperature that is below 30 degrees Celsius, it exists as what? Sodium tetraoxide 6 what? Decahydrate. But at temperature above 30 degrees Celsius, it exists as what? Anhydrous sodium what? Tetraoxosulfate 6. That's why from here to here is what? Hydrated salt. We call it what? Hydrated. Because it has 10 molecules of what? Water of what? Crystallization. So here at temperature below 30 degrees Celsius, it exists as what? Decahydrate. But at temperature from here now, look at it here. From here upwards, from 36 up to 100 and above, or above as this may be, it exists as what? Sodium tetraoxide 6 anhydrous one. So it has two, hydrated and what? Anhydrous. At temperature below 30 degrees Celsius, it exists as what? Hydrated. Specifically, sodium tetraoxide 6 decahydrate. But at temperature above 30 degrees Celsius, it exists as what? Ordinary anhydrous one, which is what? Sodium tetraoxide. No molecule of what? No water of what? Realization. Now that's the first point I want you to note. Now, so what really happened? What happens is that as temperature increases, as temperature increases, this place, it has what? Water of crystallization. That means the solubility will be what? Will be increasing as temperature what? Increasing. But when temperature is above 30 degrees Celsius, it will give up the water of what? It will do what? Give up the water of what? Crystallization, and the solubility will start going what? Down. Are we together? Are we together? That's what happened. Now let me. You can put down something. Put down something. You ask a question why, right? Now the reason is this: the salt, which is sodium tetraoxide 6. Exists as what? The salt in a solution exists in a solution as the salt exists in a solution as sodium tetraoxide 6 decahydrate at temperatures below what? Below what? 36 what? Degrees Celsius. But gives up its water of crystallization. But gives up its water of what? Crystallization. What is it? You ask question now, you keep quiet. I don't like this thing you are doing. Ask question. If I'm explaining or dictating, you missed it. Call my attention, not to keep quiet and looking at me as if you are. If that's a wrong attitude, please. It's a wrong what? Attitude. If you miss that, you do what? Ask question. Or call attention, please, sir. What did you say? Not to keep quiet as if as if I don't understand. Sit well, please sit up. Where did you stop putting that? Of course, where did you stop putting that something? Where? Seriously, I don't like this thing. I don't like it. It pisses me off. You've been together in my class for a long time. Once you don't understand something, do what? Ask question. Don't put a very wrong attitude towards it. It's wrong. Or if you miss out something, come and attention immediately. Don't. It's not to keep quiet. I was here dictating you. You stop writing. Is it right? Tell me, sir, please. This and this and this and this, please. This is where I stop. Not you stop writing. Next thing that you are fast. That's wrong, please. I think I demand apology for that. It's wrong. No, seriously, it's very wrong. It's very wrong. Let me start afresh, please. I say that sodium tetrahydrosis of a 6 shows a solubility curve with a what? Or the solubility curve of what? The solubility curve of sodium tetrahydrosis of a 6 shows a what? Shows what? A sharp break. Good. At where? 30 degrees. You ask why the sharp breaks, right? Is the sharp break is the reason for the sharp break I'm trying to do what? Explain. I've already explained it. Did you understand when I explained it? Now I want to tell you something to put down. Now start putting down something. The reason why there's a sharp break is because the salt we are in question is what? Sodium tetrahydrosis of a 6 salt. So the sodium tetrahydrosis of a 6 exists in solution as what? Sodium tetrahydrosis of a 6 decahydrate at temperatures below what? 30 degrees what? Celsius. Now, as temperature increases, it gives up what? Each water of what? Crystallization. And become what? It gives off what? Each water of what? It gives off each water of crystallization. At what temperature? Good. And become what? Anhydrous. And become what? Anhydrous. And become what? Anhydrous. That temperature at which it gives off is, listen carefully, at this temperature, 30 degrees Celsius, it transits. You can put it down. At this 36 degrees Celsius, that means that at this 30 degrees Celsius, that means at 30 degrees Celsius, it transits from sodium tetrahydrosis of a 6 decahydrate to what? To what? Anhydrous sodium tetrahydrosis of a 6. This means that at 30 degrees Celsius, it transits from where? Sodium tetrahydrosis of a 6 decahydrate to what? Sodium tetrahydrosis of a 6. I will together. Anhydrous. This point of transition is this point of transition is known as what? Transition what? Point. Are you together? This point is known as what? Transition what? Point. Is it clear? What is transition point? What point is that?
The point
at what temperature is that? It transits from where to where?
Sodium tetrahydrosis
To what?
Sodium tetrahydrosis.
Good. Now let's continue. From this I explain now. Can someone tell me? Let me know whether you are following this lecture and lectures we have been doing since. Can someone tell me what will happen? Let's assume that you cool this you cool a saturated solution. Hope you know that this is the same salt too. But because of the difference in temperature, it will start changing. Hope you know. Can someone tell me what will happen? When you cool a saturated solution of sodium tetrahydrosulfate 6 from 30 degrees Celsius down, what will happen? What will happen? Well, yeah, if it's 30 degrees Celsius, you cool it down below 30 degrees Celsius from 30 down. What will happen? It will do what?
It will become an hydrated salt.
You are trying. You have to keep going. What will happen? She tried. It will do what? Crystals of what? Hydrated salt. That is crystals of sodium tetrahydrosulfate 6 decahydrate to do what? Precipitate out. If the cooling is from 30 degrees Celsius down, the crystal that will come out of the solution will be that of what? Sodium tetrahydrosulfate 6 decahydrate. That's what will come out. But if you cool it down, from above 30 degrees Celsius, if you start cooling like from 100 degrees Celsius or from 50 or from 60 or 70, you cool it down, what will come out is what? Crystal of what? Anhydrous one now.
Yes.
What will come out is what? A crystal of what? Anhydrous sodium tetrahydrosulfate 6. Is it clear? Put it in your own word. Can you put this in now in your own word? I put it. I say that if a saturated solution, you can write. If you cannot put it down in your own word, you can write. Just let me call it for you so you can write. If a saturated solution of sodium tetrahydrosulfate 6 is cooled from 36 degrees Celsius down to temperature below 30 degrees Celsius, crystals of what? The hydrated salt, which is sodium tetrahydrosulfate 6 decahydrate, will do what? Crystallize out. However, if the saturated solution of sodium tetrahydrosulfate 6 is cooled from temperature above 30 degrees Celsius, say 70 degrees Celsius or 80 or 60 down, the crystal that will crystallize out will be crystals of the anhydrous what? Salt, which is what? Sodium. Just simply say anhydrous sodium tetrahydrosulfate what? 6. That's what we do what? Crystallize what? Out. Did you understand this graph?
Yes.
Did you understand this graph?
Yes.
I think we'll stop here. Which is that I don't think you can face anything, so you're not going to do what? Answer it. Okay? In our next class, we start with what? In fact, we'll conclude solubility in our next class. We have tried. We start with applications of what? Solubility what? Curve. The application of that will be our next class. After that, we'll talk about solubility of gases. And that will be the end of the lecture. End of solubility. We then do our review the way we did in our last class. We do ask ourselves a question here on review of what? Solubility, after which we give assignment again. Then that will be end of what? Solubility. Okay? Then in our next class, I'll see whether I can trace that passage of the paper. Let's see let me see exactly what happened in that review we did. Okay? I think that will be the review you will do in our next class. I will look for more examples on that one and trace that one. We'll do it as a review in our next class. All right, thank you very much for your attention. See you next week. God bless you.